Thanks for coming this morning. I'll try to be talking about how to fit a lot of instances on a commodity server and how to start them in milliseconds via Kubernetes. So to sort of set a preamble, the cloud is obviously great, but by now I think we can all agree that it's relatively inefficient. So as a little example, imagine I want to deploy an Nginx server to the cloud, and so naively, I might look on my local disk and notice that it's just about 1 meg in size for the binary, right? So if I want to deploy it to the cloud, one standard way I might do that is go to an AWS Marketplace, get an AMI officially from Nginx based on Ubuntu, and I might notice that my 1 meg image has gone to a couple of gigs. Of course, I can use much nicer distributions than Ubuntu, but you get the idea, and this is not ideal. And this is just the beginning of the problems, right? Imagine I want to deploy an app, and then like many apps on the web, they're intermittent. I get traffic sometimes, I don't get traffic other times, right? So what's going to happen is I'm going to deploy it, I'm not going to get any traffic, it's idle, but I'm definitely paying for it no matter what. And then later on, I get some requests, so that's good, things are active, but then the cycle repeats, it goes idle again, and I'm throwing money away, right? And so I'm paying the cloud provider money that maybe I shouldn't be paying. But then you say, okay, but if my traffic is intermittent, I can enable scale to zero. And the problem with scale to zero is that detecting when things are idle by a platform is generally slow. So your traffic may go idle in milliseconds, but the idleness detection might take seconds or minutes, and then you're running. And the activity detection of when requests come in and when things wake up is also slow, right? So the principle of scale to zero looks like this. If you're idle, you're off, great, you're not paying anything. You get requests, you go active, now you're paying, but you're doing useful work, and the cycle repeats. The practice of scale to zero is very different. First, you're idle, and the platform hasn't detected it, but you're still running, but you're paying. And then the platform detects it, you're off, that's good. But then a request comes in, and it takes some time to scale back up, in which you're paying, but you're not servicing requests. Then you're active, that's good, but then the cycle repeats, right? And then that's money again going to your cloud provider. So you might say, wait, but actually I don't have intermittent traffic. My application is always receiving traffic, it's always up. But traffic tends to also be bursty, right? And you might say, well, for that I have autoscale, right? A problem with autoscale, again, is that traffic fluctuates in scales of milliseconds, but the autoscale mechanisms take minutes to adapt, right? So the way you maybe work around this problem is you have scheduled autoscaling. You kind of assume the traffic is relatively regular, so you can sort of schedule resources around that, but of course, not all traffic is this regular. You can try to have clever predictive algorithms where maybe traffic is irregular, but you kind of predict when the traffic will be irregular, but this is a challenge. Or what most of us do is over-provision, just set resources up for peak and pay money, but it works, right? And of course, that money goes out of your budget and into the cloud provider's budget. But then you might say, okay, but I actually can have fast reactive autoscale on something like Lambda or function as a service. But then you encounter things like cold starts where your instance is down, you get some requests, it takes some time for things to sort of wake up, your users are unhappy, that costs money, and then eventually your instance wakes up and that's great, but eventually they put it back off and so forth, right? And there's some workarounds to this. One is you keep your instances warm all the time, which costs more money. Some providers have things like CPU boost where you pay more money such that the cold start happens quicker, right? But in the end, you're just paying more money. And then, of course, function as a service comes with a huge range of limitations in terms of which languages you can run, how long you can run for, and so forth, right? So you still have a problem. So the question is, where are all these problems actually coming from? Because obviously cloud providers don't like to, by design, have all of these issues, right? And if you go back to first principles, what a cloud stack looks like, you have obviously a bare metal server at the bottom, and then you have a hypervisor for strong hardware level isolation. This could be KVMs or a few others. And this you need obviously for multi-tenancy. And then ideally, you just have the application on top of that. That's probably the only thing you care about, right? And it's all within a virtual machine because that's the hypervisor model. So that's the principle. In practice, the bottom of the stack looks the same, of course, but then comes the virtual machine, and that looks quite different, right? So at the bottom, we're going to have usually a general purpose operating system like Linux or Windows, which has a lot of code that probably your application doesn't really need to run, but it's still there. You have typically a user kernel divide, which you no longer need because the hypervisor is already giving you isolation. So now you have a double layer of isolation that's providing overhead. Sometimes you might deploy a container runtime on top of that, which is another layer of isolation that you, again, don't need. And then libraries and packages and sometimes even language level isolation. And somewhere on top of that is your application, right? And the difference between the previous picture and this picture is the stuff that you don't really need and it's just kind of overhead. Not to mention that on top of that come controllers that are maybe not the fastest in the world and load balancers and all the networking part, right? So in one picture, it looks a little bit like this. You might have your little app on top and you think you're kind of lean and in control and you can fix things, but underneath you, the stuff that you don't control is this big cloud stack, right? So are these issues fundamental? And clearly not. So if we go back to the first principles where we need the hypervisor, what we want is the application inside a virtual machine and the thinnest possible layer of maybe a little bit of operating system code such that the application can run and talk to the hypervisor, right? So we want probably the leanest possible specialized VM we can. And by the way, when people deploy containers on the cloud, almost every single time, whether it's transparent or not, you have a virtual machine running underneath, right? So we'd like to somehow be able to build such a lean specialized virtual machine, and a technical term for that is a unikernel, and I'll describe that in a little bit, right? And of course, you'd also need lean controllers and load balancers. I won't have time to talk about that part. Okay, so unikernels. In a nutshell, imagine you have your application and you could sort of magically break it down into components of libraries and the kernel code underneath, and you could pick just those little bits and pieces the application needs to run and no more, and you could turn it magically into a specialized distribution and operating system just for that application. So a very specialized virtual machine, and that's a unikernel. So that's what we built with unikraft.org. It's a Linux Foundation project. Just to give you a little taste, this is 80,000 Nginx virtual machines running on a single server. We built something called Unikraft Cloud based on that. I won't have a whole lot of time to describe it, although I will demo it. Where basically you install an OSS CLI tool, and then you deploy your app with a one-liner based on Docker files, and then you get millisecond semantics. In this case, it says a boot time of 16 milliseconds. Okay, and with Kubernetes, what we did is, I'm not going to describe it in a whole lot of time because it's a lightning talk anyways, Crossplane provider, and then we can talk to the platform, and then it's demo time. Let's see how the Wi-Fi treats me. So here I have a directory of lots of applications and examples. Each has a Docker file, but in this case, I'm in the Nginx one, and I'll just use a single command, craft cloud deploy. I'm choosing a Frankfurt Metro, and then I'm going to map Nginx's default 8080 port to 443. And let's see how the Wi-Fi does. So what this is doing is grabbing the Docker file, building a unikernel, shipping it, the platform grabbed it, and deployed it. So the build time was a few seconds, and the cold boot time of the instance was 30 milliseconds. The platform detected that it was idle, so it immediately put it on standby, so it's not consuming resources. But what I can do is I can curl it here, and it'll immediately reply. And I don't know if you caught it, if you see the standby at the top, it'll go running for a second or half a millisecond, and then it'll sort of reply. And what's happening is the platform detects the traffic, talks to the controller knows that there's an instance that can handle it, brings it up, and all of that within the RTT of this connection, right? So transparent to the user. Likewise, I can do that with Kubernetes, so I have kubectl get instances. I can do, oh, this just died, of course. So let me just pop one back up, see if that works. Okay, looks like my live demo just isn't going to work because my connection died. So sorry about that. What I can show you still is I had promised 10,000 instances, so somewhere in here. What's that? I looked at, oh, amazing. There you go. So, nothing there. If I do apply, it's created, and I can just show it again. And what you might have noticed is kubectl immediately returned, so it was a millisecond start, and the thing was running. Thanks for that. And then this is a Grafana board of the server, and the sort of magic number is, well, a little bit better than promised, 10,075 Nginx web servers running. They're all scaled to 0, so as long as I don't send requests to them, they're consuming 0 memory. Okay, and then just to finish up, you can sign up if you want to sort of toy with it. It's free. And if you have any questions, I'm here. Thanks a lot for listening.
That's a wonderful presentation, and I'm really impressed that you have got a demo into a lightning talk. And I also would like to congratulate you because that CLI looked so pretty. So, you know, the outputs and everything was really well done.
Thanks.
We've got one question. What about apps which require a DS stack?
Basically, if you can describe it in a Docker file, you can sort of run it on the platform. One thing that I didn't mention is you might ask, what about applications that take a long time to start, or you know, heavyweight applications like Java or so forth? And for that, we have what's called a snapshotting mechanism, where we can initialize your app, sort of snapshot after initialization where it's at, then scale it to 0, so that when your users send the request, it's still 40, 50, 60 milliseconds to cold start.
We don't have any other questions in the Slido, but please, we still have time. I was going to ask you, what kind of industries is this kind of start, very quick start, important for?
Yeah, so either you're an end user and your application is running intermittently and you just only want to pay for when you're actually running. On the other end, if you're a company who's running cloud-prem or on-prem or servicing millions of users, one attractive thing of having this really fast scale to 0 is you have really high server density, right? So if you have 1 million users but only 100 active ones, you could potentially service all 1 million users with a single server, right? As long as the number of concurrent active users is relatively small. So you could get a lot of savings. Instead of having a server farm of 100 servers, you can run the stuff with maybe just 2.
Now, we've got a couple of questions up. And the first one is, what about Windows containers? That's why everyone was laughing.
Yeah, Windows containers, we don't support this. So this is all Linux-based. The way it works, you know, it's based on Linux binaries at present. On the open source side, there's some people adding Hyper-V support, so that will come at some point. And why not always use Unikraft? You know, let's have it. I mean, this is the relatively early technology, but eventually I think we should all be running specialized VMs. It doesn't really make sense that we take humongous distributions with general purpose OSs just to run a little app, right? That doesn't make sense.
And then there's one, I thought, interesting question. How does this performance compare to competitors, and numbers or in-house tests, if you have any?
Yeah, so for instance, cold boots, if you go to Google Cloud Run or Lambda, these things can take, depending on who you go to, could be seconds, could be hundreds of milliseconds. Here we're talking tens of milliseconds, so we're talking orders of magnitude difference normally.
And then one more question is, what's your biggest setup that you have on Unikraft?
The biggest setup, in what sense?
I think the biggest, like, amount of nodes and like the...
Oh, yeah. So basically, we have a hosted platform, so with locations in Europe, the East Coast, Center, US, and Asia. But we also we can also do cloud-prem, on-prem. So people rent maybe a Hetzner server, and we do the install, and then people just do whatever they want with that. They owned the technology.
Lovely. Let's have one more round of applause for Felipe. Thank you so much.
Thanks a lot.